This is signal generated. The input signal is sent to the breadboard. From the breadboard, the same signal is sent to both the oscilloscope and the same signal is sent to speaker that contains piezoelectric material. The speaker generates sound waves based on the input signal and the piezoelectric sensor, which converts these waves into electrical signal, which is then sent to the oscilloscope. On the oscilloscope, the yellow sine wave is input signal and the blue sine wave is output signal. When we change the frequency on the signal generator, the shape of the both sine waves also changes.
This graph represents the voltage gain versus frequency for the piezoelectric speaker experiment. The red curve with the black marker illustrates how voltage gain changes with the frequency. The first major peak at around 170 Hz shows the highest gain of around 2, indicating strong resonance. Another significant resonance occur at approximately 1350 Hz with the gain of approximately 1.5. Additional smaller peaks near 2000 and 3000 Hz suggest multiple resonant frequencies. Beyond 5000 Hz, the gain declines, indicating reduced system response at higher frequencies. The graph is essential for identifying resonant frequencies where the piezoelectric material responds most efficiently. It provides insight into the mechanical and electrical coupling efficiency of the system, crucial for sound detection, vibration sensing, and energy harvesting. Gradual roll-off at higher frequencies indicates limited high frequency response. This is the same graph, but it represents gain in decibels. This graph represents the phase difference in degrees versus frequency in hertz in a piezoelectric speaker experiment, showing how the output signal lags or leads the input signal at different frequencies. At lower frequencies like 0 to 500 Hz, the phase starts at minus 180 degree, indicating a strong lag and gradually shift towards 0 degree. In the mid frequency range, like 500 to 2000 Hz, the phase fluctuates between 0 degree and 100 degree, suggesting a complex resonance behavior. A sharp phase jump occur at 2500 Hz, where the phase abruptly shifts from plus 150 to minus 150 degree, marking a strong resonance point where energy transfer is most efficient. Above 3000 Hz, the phase stabilizes with small fluctuations. This shift highlight resonance frequencies, for example 1350 or 2500 Hz, where rapid phase transition occurs. The 180-degree phase shifts at characteristics of piezoelectric resonance, crucial for filter design and frequency response analysis. The most prominent peak in the FFT graph is at 1.356 kHz, which is likely the resonance frequency of the piezoelectric sensor or the primary vibration mode. This indicates that the piezoelectric material is responding strongly at this frequency. The strong peak at 1.356 kHz suggests that this is a resonant frequency of the piezoelectric material or structure. The decay in amplitude beyond this peak indicates that vibrations are damped at higher frequencies. The FFT graph helps identify the frequency response of the piezoelectric system, useful for vibration analysis, ultrasonic applications, or mechanical stress sensing. The oscilloscope graph presents two sinusoidal waveforms. The yellow waveform represents the input signal, while the blue waveform represents the output response of the system, likely a piezoelectric element. The blue, which is output signal, lags behind the yellow, which is input signal, indicating a phase shift due to system response time. Additionally, the amplitude of the output signal is slightly smaller than the input, suggesting attenuation likely caused by the energy dissipation within the system. This behavior is a characteristic of the dynamic system where the energy is transferred and the transform, leading to both phase delay and the amplitude reduction. The smooth nature of both waveforms resisting a linear and predictable response, which is expected in resonant or oscillatory systems influenced by mechanical and electrical properties. We have identified resonant frequencies at 170 Hz, 1350 Hz, and 2500 Hz. Therefore, we will calculate the quality factor for those two frequencies as follows. We are using a signal generator to provide input to a breadboard. From the breadboard, the signal is sent to the both an LED and an oscilloscope. A 330 ohm resistor is connected in series with the LED. When the input frequency changes, the LED's brightness also changes, affecting the light received by the photodiode. The photodiode is connected in series with a 10k ohm resistor. The voltage across the resistor is taken as the output and displayed on the oscilloscope. On the oscilloscope, the yellow sine wave represents the input signal, while the blue sine wave represents the output signal. When we change the input frequency on the signal generator, the shape of both the input and the output sine waves also changes.
This graph represents the gain versus frequency response of the photodiode experiment. The gain is highest at the low frequencies, indicating that the system efficiently responds to low, slow changing light signal. As frequency increases, the gain gradually decreases following an exponential decay pattern. Beyond 700 kilohertz, the gain drops significantly, suggesting that the system behaves as a low-pass filter, attenuating high-frequency signals. This implies that the photodiode circuit has a cutoff frequency beyond which its response weakens. The graph is crucial in understanding the photodiode's frequency sensitivity, helping in the design of optical sensors and communication systems. The observed behavior highlights the system's suitability for detecting low-frequency variations in light intensity while being less effective at capturing rapid fluctuations. This is the same graph as the previous one, but it represents gain in decibels. This graph represents the phase difference versus frequency for a photodiode experiment. The phase difference indicates the time lag between the input light signal and the photodiode's electrical output. At a low frequency, the phase difference is nearly 0 degree, meaning the frequency output is almost in sync with the input. As the frequency increases, the phase difference grows with a rapid rise between 0 to 100 kHz and a steadier increase beyond 200 kHz. At a higher frequency, the phase difference approaches 100 degree, indicating a significant lag. This behavior aligns with the low-pass filter response. Where higher frequencies experiences greater delay, the graph is crucial for understanding the photodiode circuit's frequency-dependent response, essential for high-speed optical communication system design, where minimizing phase lag is crucial. This oscilloscope graph displays two sinusoidal waveforms. The yellow waveform represents the input signal while the blue waveform represents the output response. From photodiode setup, the output blue signal exhibits a phase lag compared to the input yellow signal, indicating a delay in system's response due to the photodiode's reaction time and its circuit characteristics. Additionally, the amplitude of the output signal is significantly smaller than the input, suggesting attenuation, which is common in optical to electrical conversion due to factors such as resistance, capacitance, and light intensity variations. The smooth sinusoidal nature of both waveforms indicates a consistent and periodic response, typical in frequency-dependent experiments, where the photodiode's response time and sensitivity affect signal behavior. This is the FFT graph represents the frequency spectrum of the signal obtained from the photodiode experiment. The x-axis shows the frequency in the kilohertz, while the y-axis represents the signal magnitude in dBV. A distinct peak is observed around 50 kHz, indicating the primary frequency component of the detected signal. The surrounding noise floor appears relatively low, but there are minor fluctuations suggesting some background noise or harmonics. The sharpness of the peak suggests that the photodiode effectively detects and responds to the 50 kHz input signal with minimal distortion. The presence of the additional minor frequency components could be due to the circuit noise, external interference, or the inherent characteristics of the photodiode response. This analysis helps us in understanding the frequency behavior and efficiency of the photodiode in signal detection application. Here is the 3 dB cutoff frequency calculation as follows.